Friday the 13th.
That's real cool.
No.
So every 17 years, the October 17th is required?
So it would seem. Whereas when 17 isn't divisible by anything. Guess when I'm 34, I'll be on a Friday the 13th again.
Why is everything cold?
Did you guys see
Alright, ladies and gentlemen. So, I want to give you the data workable project. I'm a little worried because I have a bunch of other things doing your stupid recommendations and stupid short intent. So I'm a little concerned about getting all the stuff ready for that program to give you the proper cost estimate. Right now the estimate is too low. Be aware of that. Let me explain why. You have to do two things with the detector. First, you have to build the actual detector, which is expensive, right? You have to put these strips of silicon in. But then you have to do something else. What's that? Readout, what's that mean?
Right.
It's like what? Right, what does it mean? What does readout mean? You have to connect with wires from the silicon detectors to your readout boxes somewhere else, right? That requires you to run wires through, and of course you want these wires, but these ribbon wires, very, very thin, Kapton ribbon wires, extremely thin, flexible wires that you can run out of there. But you still need to build them, so they cost money, right? They don't cost a lot, but you need how many wires?
A lot.
One per channel. What's a channel? Yeah, it's each strip of silicon is one channel. If you're using pixels, each pixel is one channel. So when it tells you, for example, that silicon pixels have a density of 100 million per square meter, that also means if you have a square meter of silicon pixels, then you need 100 million wires running out of that. Okay, the 100 million wires, the individual price is not that much, but it adds up. So I gave you an estimated cost of $1 per readout channel. So that is going to drive up the price quite a bit. In addition to the, what's it, $10 million per square meter, now you also have to pay an additional $100 million per square meter for all the readout. That's why I told you if you wanted to reduce the channel density, you can. Okay, you may not increase it, that's the limit, but if you wanted to reduce it, you could. That makes your detector a little bit worse, but it does save you readout money. Okay. If I had maybe in a few more iterations of this, I'll be able to actually work in the calculate the extra material and all that stuff also adds to this and stuff, but anyway, one thing at a time. Okay, so that's important to know. Next, the main thing to do, and a big thing that separates this from last year's assignment, is that we're really focusing on getting the resolution right, okay? To make sure you can actually measure the stuff you need to measure, because you get really high energy particles coming out, so you really need to be able to measure them. So what you really need is to figure out your maximum resolution for a given set of parameters, right? The basic idea is this. Remember, every detector you can think of as a bunch of strips. They read out yes or no, right? Each one is like, I got a hit, or no, I didn't, right? They are binary in that sense. Thus, each detector, if a particle is going through, it can hit here, or it can hit here. It cannot hit in between. So the space between two strips affects your resolution. Because if you have a particle strike here and you have a particle strike here, they're exactly the same signal. And you cannot distinguish between this. Okay, does that make sense? So, what is of concern then is if you have a number of layers of detector, right? Then you have some particle go through. And what you're concerned about is the ones that have really, what particles are we trying to get? The ones we're most concerned about. Particles with high energy or high momentum. So it's the same thing at this point. But yeah, high momentum is what we're right? So we're worried about these high momentum particles. High momentum particles, what will their track look like? It will look like, they will always look like a circle because of the magnetic field. Make sure you build your magnet. The magnet typically goes around everything, big cylinder. Everything inside the cylinder will have the same magnetic field. You have to build a magnet around it, the solenoid. That's the solenoid. Okay, so you have a magnetic field, it will make things twist around. That twisting, of course, will depend on the magnetic field. So you can make the magnetic field bigger, and what happens? It makes it more expensive, and it adds material. Okay, makes the magnet has to be bigger. So you want to balance that as much as you can. That's why in the two big detectors at the LHC, CMS has a 4 Tesla magnet, and Atlas has a 2 Tesla magnet. But the Atlas magnet is bigger because you need more space now, but you're not bending them as much. So that's the trade-offs they consider. Okay, so you have a magnet. Now look, a low energy particle or medium energy particle will go like this, and you'll see it. And you'll be able to hit the points, and you'll be able to measure the curvature. So that's no problem. The problem is kind of the limiting case, the ones that are going, if something is going too high energy for your detector, what does it look like? A line, okay? So this is fine. This is bad. Actually, I can't draw straight. Yeah, that's straight. Okay? If you get a straight line, you get no measurement. Okay? So obviously, your maximum energy measurement is going to be a track that looks like what? Maximum momentum, excuse me. It's going to be a track that looks like what? Right, just barely curved, right? Just slightly curved. So to do that calculation, you're going to have to take, what you should do is take a straight line and then make it into something that's just barely curved, right? The easiest way to do it is to just pick 3 points to work with, beginning, middle, and end. Then put 3 points to the circle, okay? So if you do that, then you can have a line that is just slightly curved, right? When you say just slightly curved, what does that mean? Well, remember, you have this limited pixel spacing or strip spacing to deal with, right? So if you move this by a little bit, then you want to be able to tell the difference between them. Yes.
So like for like the middle part, you want to move the interaction point.
Not the interaction point, but the hit, right? So instead of hitting here, you see, okay, let's move over by 1 strip, right? That in principle is a different track. Now, to be fair, that's kind of ambitious. Real life is a lot more complicated than that. But anyway, let's not deal with that. It's basic solutions right now. Okay, so that you want to get your resolution measurement. That resolution measurement should drive the design of your detector. Okay, because you don't want to build too big a magnetic field. It's a waste of money and a waste of space. Right? It's not actually the money that's a big deal. If you only spend $1 billion, that's fine. But you don't want to waste the material, the space that will make your power limiter and the rest of your detector worse. And you have to blow a lot more money on those. So you want to get this thing at a resolution that you want, but you also want to save money, right? Or save space more than anything. Okay. Now, so this one is your max. Okay, so I'll let you work on it. The main thing is, for your calculations, choose 3 points, but please, in your actual detectors, put more than 3 layers, okay? Put substantially more than 3 layers. Like, I don't actually have a number, but all the ones I've worked with use more than 5, certainly, okay? Because of the multiplicity that, if you have a proton-proton, or anything with protons in it, anything with hadrons, you're gonna, or let alone you guys, you're gonna want real high-resolution stuff here because you need to tell the tracks apart. Okay, so high resolution close to the beam pipe is absolutely essential. If you have muons, there's still going to be a good number of particles, but you have a little bit more laxness. And the muon detectors usually focus more on getting a really nice energy momentum measurement on the curve. But don't just go with 3 and say, oh, that's all we need. You need minimum 5 and really more than that. Because of the multiplicity of particles and the fact that these things are not 100% efficient, they miss 5% of the time, and so you need to be able to work all that in so you can actually detect what's going on. So you put in multiple ones to give like reinforcement, also be able to tell different tracks apart. One more reason you need good resolution close to the beam pipe. There's a special kind of interaction that has a long lifetime where basically you have the main interaction point, the primary vertex, and then some tracks that come from a secondary vertex. That's due to a relatively long-lived particle that goes this far. How far is this? About a millimeter. So what you want to be able to do is have a sensitive enough tracker, precise enough tracker, that it can trace the tracks back and figure out that some of them came from a point a millimeter away from the other point. It requires a lot of sensitivity, right? So that's another reason you need multiple layers and lots of resolution. Okay. High resolution near the beam pipe always. That's always the most important part. Yes, Emily? You don't, so just put some stuff in. But I'm just saying, don't put 3. That'll be silly. Okay? 4 than 5. Yeah, I mean, kind of fill up the space. More silicon is generally better. Okay, general rule. Remember, you can't put the silicon in closer than 2 centimeters. Okay, they need cooling space. Silicon runs hot, so it needs to be cool, otherwise it melts, which is very bad. Yeah.
When you mean like closer than 2 centimeters, so like separate.
Radially, right? So if you're doing concentric, I'm sure you're doing concentric something, right? So concentric cylinders, for example, need to be separated by 2 centimeters, like going outward, radial. Okay. If you're doing boxes or spheres or stars or whatever, it's still the same thing. It's still 2 centimeters. Okay, one more thing, just because I just want to make sure we get the basic design. Now, you can always modify the basic design. I just want to make sure you understand what the basic design, the traditional design is. Big solenoid on the outside, because that provides a magnetic field. Anything that's outside of the solenoid cannot be used for momentum measurement, because there's no magnetic field there. Everything inside is what you can use. The solenoid has a thickness that you can see, right, that's based on its field strength, but that's like the thing itself. And then you pay for all the stuff contained inside. The volume is what you pay for. So it has a price per cubic meter per Tesla. So everything scales linearly with the amount of volume in the year and the amount of magnetic field you put in. Okay, and then inside, you put, in a traditional design, with a bead pipe here, you put concentric cylinders around it. The cylinders sometimes get longer, sometimes don't, as they go out. That's just sort of follow the angles of the particles. And then you have some particles that go straight out like this, okay? And your concentric cylinders won't do very well on those. So these cylinders, when I say cylinders, they're just the size of the cylinder. That's what I mean, like just this part of the cylinder, not the caps. So they typically build on, basically, caps, discs that slide into the end like that to catch the stuff that goes straight out. Okay? You would need, if you really want a good measurement on these, you would need approximately as many layers this way as you do that way. But some of the stuff kind of goes through both. You see, it hits some barrels and some discs. They call these barrels and discs. So it hits some of the barrels and some of the discs. So this is a traditional design. This is like what CMS and Atlas use, for example. But someone asked, does creativity matter? The answer is yes, but accuracy matters more. So in other words, the most important thing is that you do it right, you get a good, sensible resolution measurement, and that the thing works to measure what you want. But it'd be nice to do something that's not just a duplicate of what CMS does, because you do have like 3 times as much money as they do. Yeah. Yeah, this is all silicon. CMS is all silicon. Atlas puts silicon and then tracker around it. Multi-wire tracker around it. Yeah.
I think the volume for the solenoid, we all can assume that it's going to be a cylinder or yeah.
Solenoids basically have to be cylinders. If you want to make it, I mean that's what solenoid means. But if you want to make a different shape, there are options you can talk about. Okay. We can talk about options. There are other ways to make magnetic fields and other shapes you can use. But solenoids, the basic solenoid is a cylinder. If you don't make a cylinder, it doesn't work right. Yeah.
What's the downside of
you add on a lot of material. Remember, the colorimeter is up here, and you want as little material between your bead-pipe colorimeter as possible. But obviously, you have to have some. So an overly thick solenoid wastes space, wastes money, and adds extra material, making a colorimeter measurement worse. But of course, you need one in there, or you need a magnetic field somehow, or else you're measuring nothing. Yeah.
So the colorimeter is what measures the energy,
Energy.
and that's outside?
Typically. You could try to put it inside, but then you can't measure the tracking very well. So it's not very useful. Okay. So right up is fine. The spreadsheet is just a spreadsheet. You just follow what's there. I figured out how to compile for Mac, but I haven't gotten it all working last night because my son wanted to play with Daddy, and now when he wants to play with Daddy, he wants to play Zelda with Daddy, and Daddy is like really easy to convince. So, point is, so I didn't get as much done last night as I wanted to. Well, I got some stuff done, but it wasn't for your class. So, the craziness around the Switch has finally gone down, so we could actually buy a big thing and have to get Zelda. So, anyway, I wanted to do it during the summer, but anyway, moving on. So, actually got it right after you guys got to the test and you did that thing problem. Anyway, I'll try and upgrade this thing over the weekend. I will email you of this sort of visualize. The cost calculation isn't right yet, so I need to fix that. And I almost have it done, but I haven't done it yet. Okay, so that's what's going on. The resolution measurement, material measurement, I just want you to tell me how you did it, right? On paper or a computer, however you want it, but I need it digitally eventually, right? But if you want to, if it's easier to write it out and then scan or take a photo of that or whatever, it's fine. Okay, so yeah. It's just written out. I did this, I calculated like this, and so this is where I come from, right? Remember, of course, that when you do your equation, P equals QBR, right? You have to do that all in SI units. So what you do is do all this stuff in meters, take your magnetic field in Tesla, the charge of 1.6 to 10 to the negative 19, right? Put all that, you get an answer in kilogram meters per second. Then remember the conversion you want, some people mess this up, it's very important. And the conversion you want is from kilogram times meters per second to GeV over C. If you put that into Wolfram alpha, it will do it right. Okay? But that's make sure you convert to GeV over C. Not the conversion from joules to GeV, which is off by a factor of C. Okay, so do it this way, you'll get the right conversion. And then once you're in GeV over C, energy is the same. You don't have to, well, you're actually anything but energy anyways, right? So once you have that, that's the number you want to quote. Now, of course, I want the momentum in GeV. I don't even know what a kilogram meters per second is. But you have to do your calculations in those because you need meters and stuff like that. Make sense? Okay, ask me questions. Go to work.
Okay. What if? Hang on. What if? So you know?
So we need to do.
Wait. So you know how like we can like do basically any shape we want for the thingy, for the detector.
That's what it's hard if I understand about that.
Not like for the solenoid, but for like the detector. You know, like let's see.
Yes, although there are some that are easier on me and
Okay, but what if we did it in the silhouette of Dr. Dong and had a bunch of...
your decision. Your decision. She thinks we need to make the detector in the shape of Dr. Dong. I think Nolan speaks for both of us very loudly.
So how exactly are we doing?
What if we did something dumb like
exactly
a cat or flower or star or something
very similar
or you just want to
to-
do like a cylinder.
I thought we were going to do a sphere.
Oh yeah, or a sphere.
Something similar to this. You have your pipe. You have your four. What the heck?
4, 3.
You have your four pipes.
No! All my calculations are
Why?
Okay, like that. Right? Then what we're gonna have is we're gonna have it go like this.
See, look at my math.
You're gonna have.
Oh boy.
You don't have to worry too much. You don't have to worry about the
First of all,
size of the thickness of it.
Solenoid. It's gonna be like doink, 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 doink.
Oh, so make a cylinder that just goes up
80,
and down.
73.
first of all, how big?
Yeah. Because this is where the collision's gonna happen. It's gonna come out like this. Yeah.
Yes.
And then you're just gonna have that expand for 2 meters. And we'll do that about minimum of 5
Well, this was the
times.
Any big adjustments to the beam pipe thing? Okay, the beam pipe size. If you had same charged particles colliding, such as proton, then the beam pipe radius is 4 centimeters, like I said. That's like the reason is that's actually pretty big, and the reason is because you've got to that final step where you take the two beam pipes and fuse them into a single one requires space sort of for the magnets to get them together. Okay, so because that the beam pipe has to be fairly large to allow sort of room for the beams to maneuver. However, if you have opposite charge, proton, antiproton, or positron, electron, or whatever, muon, etc. If they're opposite charge particles, then the beam pipe can be down to 1 centimeter.
We're doing this.
That's because they're already in the same beam pipe, so they don't need to do a weird maneuver again. There's no double beam pipe.
Is that what food was? Wouldn't muon, anti-muon make
just so you know,
nothing?
No.
I will try to update the document, but you all heard it from me.
That's
Yeah, sorry.
matter and antimatter. When you switch matter and antimatter together, that's going to be more.
Which do you...
Anyway, so we got.
There was a reason he told me, but the solenoids had to be arranged like this for some reason.
And each layer has to be 2 centimeters apart.
Let's start with the biggest layer in Word, or do you want to put the index layer in Word?
How many layers do we want? How many can we have? How many can we afford?
He's
56.
He has 12, I think.
Only 12?
No, less than that.
Less than that.
Well, if it wasn't for the fact he said 2, 3, 2, 3, that's 5. It's 5.
I think really high resolution right near the source, and then they'll gradually decrease to lower resolution in the middle, and then they'll be resolution on the outside.
So like
that. So we sort of have a start and an end point, then we can get a general idea of that.
yeah, we can use the outer points and the inner points to make the curve.
Yeah.
You only need 3 points to make a curve, right?
Yeah.
Okay. So basic shape.
Cylinder, 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 cylinder.
It doesn't make it actually is easier for me.
I still think we should do Dr. Dog shapes.
You'll present that idea.
He's all the way over there. I can't do it. That would be a bad idea.
You don't have these things called layers. Anyway, width and radius.
Well, first we have to figure out what each layer is going to be.
This is right on, because you can stick it pretty much right on.
This is the innermost layer. This is the it's one of the main connectors. How many layers do we need? And what does ISL stand for?
How many layers can we afford? Let's do that many.
We can't. I can't calculate that.
No, let's do 11.
Because if you're going to make the cylinder
11 for now. Okay. What does ISL stand for?
No, particles move through the beam pipe.
Yeah, but I'm saying that if we build the cylinder,
Not on his page. It's scary.
it has to come through here.
He has it on his thing, and I don't understand what it's used for.
And then the same, this
ISL too.
Yeah,
Already
it's going to be
did.
going through
Is it on here?
thing
No.
4 ways, so you're going to have to do this thing on each of the 4 things. It's the same accommodations that you have to do for a cylinder.
How did he know we're
Except
doing
now
the
it's 4 dimensions, or 3 dimensions.
Probably a lot of
We're not including time in this, or fuse.
that, or since our last project
Okay,
was
so we have-
least concern for us.
We have the length of this, okay?
By the way, who has the lowest grade?
Radius.
80-ish.
I have less than that.
I have less than that as well.
I have less than that as well.
Do you have less than 70?
No.
No.
Less than 75?
I think it's edging that.
Wait, maybe I do have less than 70 actually.
Wait, why are we
It's not including your final.
What do you mean, my friend?
We're deciding who gets the extra credit points for the spreadsheet.
Already got that. Oh, I have 73.
Oh, fine, I have to sign back in again.
Alright.
I have an 83.
What?
83.08.
Wow, you're doing so much better than me. Why Nolan? Okay, it's you that gets it then.
But I don't know how to do things. What was the thing again? Heck, I'm not smart enough for this crap.
So it's always better to know that they're close.
Put in the number of accelerators.